Welcome to e-learning. I am M. Nandini, Assistant Professor, Department of Electrical and Electronics Engineering, Thandai Periyar Government Institute of Technology, Vellore. This video lecture is related about three-phase inverter with 180-degree mode of conduction. Inverter is a device which is used to convert our DC voltage into the AC voltage. Likewise, three-phase inverter is also used to convert our DC voltage into the AC voltage. So mainly the three-phase inverters are used in the industrial application for providing a adjustable frequency power. Three-phase inverters is also called as a six-step bridge inverter because it uses minimum of 6 thyristors. Each thyristors are turned on or gated at a regular interval of 60 degrees. This is the circuit diagram of three-phase inverter. Here we have a 3 thyristor, namely T1, T2, T3, T4, T5 and T6. So here the commutation circuits are not shown because of our simplicity. Here the T1 and T4. It is the first term of the inverter. T3, T6 is the second arm of the inverter. T5, T2 is the third arm of the inverter. Upper group thyristor is T1, T3, T5. Lower group thyristors are T4, T6, T2. So all these thyristors are connected with the supply and also connected with a three-phase star load. Next is the conduction mode of the three-phase inverter. Here the 3 half-bridge inverter are arranged side by side and connected to the star load. Here we have 2 possible patterns of gating the thyristor. One is the 180 degree mode of conduction and another one is the 120 degree mode of conduction. In case of a 180 degree mode, each thyristor is turned on at an interval of 180 degree. In case of a 120 degree mode, each thyristor is conducted at an interval of 120 degree mode. In this video, we gonna see about 180 degree mode of conduction. So for a 180 degree mode of conduction, each thyristor conducts for a 180 degree of a cycle. Thyristor pair in each arm, that is T1, T4 is the first pair, T3, T6 is the second pair, T5, T2 is the third pair. Each are turned on with a time interval of 180 degree. That means if T1 conducts for 180 degree and T4 for the next 180 degree of a cycle. Thyristor in the upper group. For upper group, we have a 3 thyristor T1, T3, T5 that conducts at an interval of 180 degree. It implies that if T1 is turned on at angle of 0 degree, then T3 must be turned on at angle of 120 degree and T5 at angle of 240 degree. Same is repeated for other group of a thyristor. Based upon the turning on condition, the table is drawn here. For step 1, thyristor T1, T6, T5 is turned on. For step 2, thyristor T1, T6, T5. So this is the step 1. This is the step 2. For step 2, thyristor T1, T6, T5 is turned on. For step 3, thyristor T1, T3, T2 is turned on. For step 4, thyristor T4, T5, T2 are going to be conductor. For step 5, thyristor T4, T3, T2 are conductor. In step 6, step 6 thyristor T4, T6, T5 are conducted. So in this first table, the first row shows that T1 from upper group conducts for 180 degree and T4 for the next 180 degree, and then again T1 for 180 degree, and so on. In the second row, T3 from the upper group is starts for conducting 180 degree. After T1 start conducting of 120 degree. After T3 conduction for 180 degree, T6 conducts for the next 180 degree, and again T3 for next 180 degree. Further, the third row, T5 from the upper group start conducting 120 degree after T3 or 240 after T1. After T5 conduction for 120 degree, T2 will start in the conducting of lower group. So in this manner, the pattern of firing the sixth thyristor is identified. This table shows that for a step 1, we already told that for a step 1, T1, T6, T5 is turned on. Likewise, all 6 steps, each thyristor is turned on. So based upon this, we drawn an equivalent circuit for step 1, step 2, step 3 and step 4. In the circuit, here the circuit is for step 1. In the step 1, the thyristor T5, T6, T1 are turned on. Here the T1 is 1, next 5, 6 are in a closed condition. Other thyristors are in a opened condition. So these are shown as a closed switches, and non-conducting thyristors are as a open switches. The load terminal A, C are connected to the positive of the load terminal A, and C are connected to the positive of the supply, and B is connected to the then C is connected to the negative of the supply. The magnitude of line and neutral voltages can be obtained by using a formula VC0 is equal to Vs by 3. So this can be obtained by using a voltage division rule. So same wise, VB0 equal to minus VOB equal to minus 2Vs by 3. So here also for a step 2, the thyristors 6, 1, 2 are conducting. So the thyristors 6, 1, 2 are in a closed condition. Other non-conducting thyristor are in a opened condition. So same, the A and B are connected to the positive of the supply, and C is connected to the negative of the supply. So here also we gonna find the VA0 equal to 2Vs by 3 from the diagram. By using voltage division rule, the VA0 is equal to 2Vs by 3, VB0, VC0 equal to minus Vs by 3. Same way, the step 3, step 4, step 5 and step 6, we're going to calculate the voltages VA0, VB0, VC0. So from the finding value, the output phase voltage waveforms are drawn here. For during 0 to 60 degree, the VA0 value is the Vs by 3. Then during 60 to 120 degree, the VA0 value is the 2 Vs by 3. And also for during 0 to 60 degree, the VB0 value is the minus 2 Vs by 3. So during 0 to 60 degree, the VC0 value is Vs by 3. So by finding the all value in the equivalent circuit, by using that, we are drawing the output phase voltage waveform. So next is the output line voltage waveforms. So for 120 degree, for the period, the output voltage VAB is equal to VA naught minus VB naught. For this, the value minus Vs. For this 60 degree, the value is the minus Vs. So likewise, all the 360 degree having the value of Vs and minus Vs according to the conduction. So next we're going to see the output voltage equation. So during step 1, so we already told that during step 1 the thyristor 5, 6, 1 are in a conducting mode. So from that we're going to find the current I1. So we know that what is the formula of, by using a Kirchhoff by using a law, Ohm's law, I is equal to V by R. Here we use a impedance value. So Vs is the supply voltage. So Z here. So Z, and from these two are connected in a parallel. So we taken this as a Z by 2. So after simplifying this, we get 2 Vs by 3 Z. So next the line to neutral voltage R, that is the VA naught VC naught equal to, so same formula I into R. So I1 into Z by 2. Here R is the Z by 2. So substitute the I1 value here, then we get VA naught VC naught equal to Vs by 3. So the neutral voltage is also written as a VA naught equal to VC naught minus Vs by 3 and VB naught minus of 2 Vs by 3. So the value of VA naught, VB naught, VC naught is could be calculated for each step by using the equivalent circuit. So from that, all 3 line output voltage can be described by using a Fourier series. The VA naught AB equal to summation of n equal n equal to 1, 3, 5 up to infinite 4 Vs by n pi cos n pi by 6 sin n omega t plus pi by 6. So each phase output voltage is same, only the angle will be differed. So next is the Fourier series expansion of the line to neutral voltage. That can be expressed by VA naught equal to summation of n equal to 6k plus or minus 1 up to infinite 2 Vs by n pi sin n omega t. Here the k value is up to 0, 1, 2, infinite. So same wise VB naught, VC naught value is same, only the angle is differed. So from the equation VAB, the RMS value of the nth component of line voltage is described by VLN n equal to 4 by root 2 Ps n pi cos n pi by 6. After simplifying that, we get VLN equal to 0.7797 into Ps. The RMS value of line voltage VL is calculated by using a formula VL equal to 1 by pi integral of 0 to 2 pi by 3 Vs square into d omega t whole power 1 by 2. After simplifying that, we get root of 2 by 3 Vs. Then simplifying that, we get 0.8165 into Vs. This is the RMS value of a phase voltage. Vp is expressed by Vp. We already know that phase voltage is equal to VL by root 3. Substitute the VL value. Then we get a root 2 by 3 into Vs. Then the RMS value of fundamental phase voltage from my equation VA naught is Vp1 equal to 2 Vs by root 2 by pi. So after simplifying this, we get 0.4502 Vs. We know that Vs value is the VL1 by root 3. So in this video, we are going we are discussed about a 3-phase inverter with 180 degree mode of conduction and output voltages and equivalent circuit and related equation. Thank you for watching my video.